Hello there, this is Mixo, and today I'm going to be explaining like Sudoku concept that I've used in one of my recent puzzles, which is like sort of a variation of a specific Oddagon pattern. So I'm first going to explain the Oddagon pattern and then the variation that I've used and how to think about it in a more theoretical way, I suppose. Although when I say theoretical, I'm not gonna use the typical like theoretical Sudoku terminology, so we're not gonna talk about strong links or anything like that today. I'm going to intuitively explain this pattern for people who are used to solving variant Sudoku, like using Snyder notation. Okay, so first we're going to start with this pattern. So what I've done here is I've used the corner mark notation, so it means that in this case the digit 1 in each of these 6 boxes where I've marked the ones is supposed to be forced into one of 2 places in each box, so 1 cannot go anywhere else in these boxes. And I've arranged them in such a way that there's like a loop, so I could start from this box and then go up here. I see those ones are exactly vertically aligned with each other, and then I'm going here, these are horizontally aligned. I'm going down here, again exactly vertically aligned, and so on, and at the end this like forms a loop around the grid. And I've also put each of the ones in diagonal offset from each other. Okay, so a very specific pattern in this case, and we're only going to look at this kind of arrangement today. So yeah, and I'm going to claim that this pattern is broken. Like there's no Sudoku, or there's no valid Sudoku grid that fulfills these conditions. And yeah, we can find that out just by trying, because we only have 2 options here. I can just start with a 1, let's say here, and then follow it around the grid, like it gets placed in all of these pairs, and now this pair does not have a place for 1 anymore because both of them are ruled out, right? And if I started with the other place, like this, the same thing happens. So by trial and error we can see that this is broken. And now instead what I want to do is, instead of trying both options individually, I want to try both at once. Or in other words, like in variant Sudoku solving, we disguise this as coloring, right? So I'm just gonna make this like a red and a green circle here. And I'm gonna say, okay, I know either the green circle is 1 or the red circle is 1. And then if I go up here and color them like this, now I still know either all the green circles in the grid are 1s or all the red circles in the grid are 1s, right? Because if I make this one, that's 1. If I make this one, that's 1. So I get this equivalence. And then I can just continue like that, going through here. So essentially I'm just doing both options at once here. And then what I see is I went from here around the grid to here, and now I have a clash, right? Because I cannot make all the green circles 1s, or I have 2 ones seeing each other here. But if I made all the red circles 1s, then these ones will see each other. So we can see this way that it's broken. And yeah, now there is a theoretical reason behind this. And we didn't need to do this color, specific coloring to see it. Like we could just look at this pattern and tell, okay, this is broken. And the way to look at that is looking at the orientation of these pairs. Sorry. And we can see that we have the green orientation 3 times and the orange orientation 3 times here. So we have an odd number of both of these orientations, and that is the condition for when this is broken. So if we had an even number of green and an even number of the orange pattern, like for example, if we flip this around like that, then it would not be broken. But if it's an odd number of each, it is broken. Yeah, this is the rule for this specific pattern, and I'm quickly going to explain why that is the case. Let's say we started with a grid where all the pairs have the same orientation, like in this case, they're all the same green pattern. And then if we do our coloring from before, for where either all green circles are ones or all red circles are ones, if we look at two adjacent pairs here, we can see that the coloring gets swapped around, right? Like if this is green-red, then this has to be red-green, because the top left and the bottom right cell are vertically aligned, so they have to be different in both of these patterns. And because we have in total an even number of these patterns, just by how the loop structure works, right? We're always going like vertically and horizontally, so we have an even number of these patterns involved in total. And each time we're flipping the coloring around, when we go from one to the next, it means that in the end it's gonna work out and we don't get any clashes here. Now, if we were to flip one of these around, so let's say this one, we instead of having the green pattern, we're gonna change it to a purple pattern. Now what's gonna happen is we're gonna break the whole thing, because this red forces this to be green, this green forces this to be red, and then here these are clashing, right? And you can think about it that way. When you have a valid pattern and then you flip one of the pairs around, you get an invalid pattern. And then if we were to flip another one, like for example this one, we're flipping it like that. Now suddenly it's gonna work again, right? Because we're flipping again, and then we can just fix this one. Okay, so I hope the intuition is there, like why this works. So basically every time we flip one of these around, we go from broken to fine and from fine to broken. And because the initial position with like an even number of each pattern is fine, means that every case where we have an even number of each orientation is fine, and when we have an odd number of each orientation, it's broken. Because we can just like iteratively get there by flipping the patterns around. Okay, yeah, at least that's the way I find intuitive to think about this thing. Okay, so that's for this specific Oddagon pattern. Now the version I used in my puzzle is a bit different, and we're gonna explain it here. So now what I've done is, first of all, A, B, C, D, E, and F stand for any sequence of digits. So you can replace them with any digits that you want, it doesn't matter, of course. And now I'm using center mark notation, so these two cells contain an A and a B, and we just don't know the order, right? These cells contain a B and a C, C and a D, and so on, right? And other than that, it's the same, the exact same cells that I also used for the initial Oddagon example here. Just now that I'm using this sequence of digits, and it goes like I'm starting with an AB pair here, and then I'm changing, like I'm still using the B here, but using C, so AB, BC, CD, DE, EF, and then back to FA. So we have this loop now with the sequence of digits involved. And I'm gonna claim that this these patterns follow the same logic as the oddagons. So if here we have an odd number of the this orientation and an odd number of this orientation like before, it means that this is broken, right? And we're gonna show that by just showing that this is essentially equivalent to the Oddagon pattern. We can use a similar way of coloring. So we're just gonna start with red and green again. Now the red and green is gonna mean a different thing. Like in the Oddagon pattern, red and green meant one of them is 1 and the other one is not 1. Here it's gonna mean, is it a letter in the odd position in the sequence of letters that we have, or an even position? So our sequence like A, B, C, D, E, F. So A, C, and E are gonna be one color, and B, D, and F are gonna be the other color. Okay, we just don't know which one is which. Now, because we know this pair is also a red-green pair, because B and C are different in different groups, and because the B is shared here, means that if that's B, this is B, or if this is B, that's B, right? So we can see that the coloring behaves the exact same way like in the Oddagon case. We can't have the reds and greens aligning, because then the B's are gonna clash, right? And now this is gonna lead to the exact same coloring like before, because we have to make sure red and green don't see each other in these pairs, just like before. And so we end up with this. And then we get the exact same clash as in the Oddagon case. So here we can see either red is the odd letters, then both of these are A, or green are the odd letters, and then both of these are A. So yeah, once again, it's broken. And yeah, like that's all you have to see. And yeah, the reason why it's broken, if there's an odd number of each orientation, is the exact same like with the Oddagon case, because like I just explained, the coloring, how it propagates, behaves exactly the same, right? So here again, we could start with, in this case, 6 pairs with the same orientation, and we would get no problems. And then if we flip an odd number of times, we would get broken grids in each case. Right, so that's the idea. And now I'm just gonna show the break-in for my puzzle that uses this, or where you can use this technique. Now I recommend you to try this one by yourself if you haven't solved this puzzle, because it's more fun that way, I think. And then you can look at if you use the same technique as I intended here or not afterwards. Okay, so a real quick explanation of the rules. As I said, I'm only gonna do the break in here. So we have thermometers. That just means that the digits form an increasing sequence along this. So like this digit is smaller than that digit, smaller than that digit, and so on a thermometer. And then we have quadruple clues, those circles with the numbers in them. They just tell us that those digits that are in the clue have to be placed somewhere in those 4 cells surrounding the quadruple clue. Okay, so the break-in idea here is the following. We have this 1, 2 quadruple, so we need to put 1 and 2 somewhere here. But that means this bulb of the thermometer cannot be 1 or 2. It's at least 3, which means that these digits are also not 1 or 2, because they have to be bigger than 3. So the 1 and 2 go into these places. Then we can do the same thing down here. We have 8, 9 in this quadruple. We cannot put 8 or 9 on the tip of the thermometer. So these digits are smaller than 7. which means 8 and 9 go here. Then we look up here. We need to use a little trick here first that anyone familiar with quadruple Sudoku is gonna know, because we have in this quad there's a 1 and in this quad there's a 1. So we have 2 1s somewhere in these 8 cells, but we only have 2 1s in these 2 columns, right? So the 2 1s in these columns are in these 8 cells, because we need to put 2 1s in these cells, which means that there's no 1 in particular in this cell. Because if we put a 1 here, we would get 3 1s in 2 columns. That doesn't work. So this digit is not 1, it's also not 2 because of this quad, so this is at least 3. Meaning this is at least 4, 5, 6. And then this digit cannot be 9 for the same reason. We have 2 9s in these quads, which take up all the 9s in row 3 and 4. So this digit cannot be 9, it cannot be 8 by the quad, so we just have these options here for the thermometer. And so our 2 8 pair is here. And now we are gonna color these pairs in. Now down here we also have to place a 9. 9 cannot go along a thermometer unless at the tip. So 9 is in one of these squares. But the 1 cannot go here because it's this digit would have to be smaller than 1. So 1 is in one of those 3 squares. And now here we can apply our technique. If we were to put the 1 into the purple cells here, we would get a 1 9 pair in these cells like that. And now we have exactly our weird chain thing case, Oddagon-adjacent chain, whatever you want to call it. I asked around before, it seems like it doesn't have a common name. So yeah, now we can see we have this chain 1, 1, 2, 8, 9. That's set up in these pairs, and we have an odd number of the purple orientation, an odd number of the green orientation here, which tells us immediately that this is broken. Now, when I made this puzzle, I definitely didn't intend for people to know this theory behind the technique. So there's also, since these are only 4 of the arrangements, you can just follow the chain around if you want. So like if we made this a 1, that would be 2, that would be 8, that would be 9, and we've ruled out 1 and 9 from this square. And similarly, if this was a 1, then this is a 2, this is an 8, and this is a 9, and we've also ruled out 1 9 from this square. So you can definitely see it in that way. But yeah, the real intended deduction, or the coolest way to see it, let's say it that way, is seeing that this cannot be a 1 9 pair. So the 1 cannot be here with the 9, placing the 1 here, and then that's gonna disambiguate the whole pattern just like that. Okay, yeah, and that's as far as I want to show it. If you tried solving this puzzle, I hope you enjoyed it, and if you haven't, it's still worth continuing here. There might be another interesting thing along the way here for you to discover, even if you've just let me spoil the break-in for you. So yeah, I hope you enjoyed this video. It's the first time I'm trying to record something like this. It's a lot harder to explain on camera than I expected, so hopefully it wasn't too bad. And yeah, maybe I will record a video again sometime if I have a good reason to. So yeah, hopefully you enjoyed it, and see you next time.